Hi class, welcome back. Today we're going to discuss integration by substitution. Integration by substitution is a special technique that is used when we have a special circumstance. We'll discuss today what are those special circumstances and how to apply it, what technique to use, and we're going to show you two different techniques that you can use, and you can choose which one you prefer. There's a benefit for each one, and so either one will actually give us the same result. The objectives are to use pattern recognition to find an indefinite integral, use a change of variable to find an indefinite integral, we're going to call that u substitution, and then use the general power rule for integration to find an indefinite integral. Use the change of variable to evaluate a definite integral, and evaluate a definite integral involving even or odd functions. So we're going to start here first with pattern recognition. In this section, we'll study techniques for integrating composite functions. The discussion is split into two parts: pattern recognition and change of variables. Both techniques involve u substitution. With pattern recognition, you perform the substitution mentally, and with change of variables, you write the actual substitution steps. The role of substitution in the integration is comparable to the role of a chain rule in differentiation. Recall that for a differential function given by f of u, where u is g of x, then the chain rule states that the derivative of f of g of x is equal to the derivative of the outside f times, leave the inside as it is, g of x, and then at the end multiply by g prime of x. So we see here that if we apply the derivative of this when we have a function instead of function, then we have to just apply the chain rule. So we do the derivative of the outside, leave the inside as it is, and then multiply by derivative of the inside. Now, if you notice here, if we apply the technique that we discussed before, and we said, hey, well, what about we apply the antiderivative on both sides of the equation? What would happen? Well, let's do that. So we apply, let me use a blue color here, the antiderivative of the left. You have to do the antiderivative of the right. Obviously, we'll add the dx here, and dx there. Now, what happens to the left is that this will cancel each other out. And so you're left with just this part right here. This part right here. Right there. Do you see that? Which happens to be this part right here. Now, because technically we did the antiderivative of a function, we're technically going to get a plus c. So we'll add the plus c at the end. But if you notice, on the right side of the equation, we end up getting the antiderivative of this. So we're going to write it over here. So this is actually amazing, right? Because we just learned a new technique just by working backwards from the chain rule. Now, does that mean that this is the chain rule process? We're doing the antiderivative chain process? Well, not necessarily, right? It's just sort of working backwards of the chain rule. So this is the antiderivative of the result of doing chain rule. I hope that makes sense. So this is the result of doing chain rule. And what we're doing is we're taking the antiderivative of this, and we end up getting the original function. So, but if you guys notice, what needs to happen in order for us to do this is the following. You need to have the derivative of the original function. So from here to here, you see what happens? From here to here, you're basically taking the antiderivative of the function, and that's how you get this. And then you rewrite g of x inside that function, and then this part goes away, right? This part goes away. But if you guys notice, two things. We need to have this part and this part happen, meaning you need to have the derivative of the outside, and you have to have an inside function. and then outside you need to be multiplying by the derivative of the inside. So we must see those two things. A lot of times we often just focus on seeing the inside function and then outside the product of the derivative of the inside. And it's very easy for us to make the notation or the note just like what we had it for the derivatives. And so we can generalize this with the next theorem. Theorem 4.13. The anti-differentiation of a composite function states that let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable, meaning the inside function, on its domain, and f is the antiderivative of f on some I, then the following is true. If you have a function and then you have an inside function and then you have the product of the derivative of the inside, then the following is true. So you must have those conditions. Do you see what happened to f? F is nothing to worry about, because when we know what f is, the outside function, all we have to do is take the antiderivative of it and then keep the inside as it is. All we have to do is make sure that this is happening outside the function so that this can happen. An alternative way to do this is by making a u substitution. So this is sort of like the second technique. We can try to do this and look at the pattern, or we can use u substitution. And the u substitution, what it tells us is it sort of kind of makes it easier for our eyes to follow. So what I'm saying here is, if you let u equal g of x, so that means that this will be your u, then that means that du, the derivative of u, will be g prime of x times dx. Well, what happens here is, if you replace g of x with u, and then you replace g prime x dx with du, as stated here, then if you notice, we just made the problem much easier. These two are the same problems, except that this looks easier to our eyes. It looks more familiar, and we feel more comfortable on taking the integration of this. And so then we can take the antiderivative of this by saying, well, the antiderivative of this function in respect to u will be uppercase f of u plus c. And then, as you guys will see in the next step, we'll replace u back into the equation. So this is a step that is only done to make the whole process look easier. Let's try example 1. Example 1 shows how to apply theorem 4.13 directly by recognizing the presence of the composite function f of g of x and g prime of x as a product. Note that the composite function is the integrand that has an outside function f and an inside function of g. Moreover, the derivative g prime of x is present as a factor in the integrand. So here is our integrand, what's inside the integral. Here's the outside function, here's the inside function, and here's the derivative of the inside. And the result will be the antiderivative of the outside function, and we just carry the g of x. And that's it, and this goes away, right? But that needs to be present. The exact combination of this needs to be present just like it is, exactly as it is, in order for this to happen, right? In order for us to find the antiderivative. Now, if you notice, what is this going to do to the problem is it's going to allow us to open the door to other functions, right? Because so far, if you guys remember, we were limited only to finding derivatives that were specifically power rule, addition, subtraction, trig functions, and sum and differences, right? But now we're able to now find a derivative when we actually have a product. In fact, also a function instead of function, so even more. So let's try example 1. So first we're going to recognize that this is the integrand. The integrand has a square function, right, of x squared plus 1. And then outside, there's a 2x product, there's a factor of 2x dx. So my suggestion, and this is probably the most consistent rule, is that we have to recognize what's your outside function and what's your inside function. If you look at this, notice that there is a squared function happening. Inside you have another function, and that's how I recognize this. So in the first part, I sort of recognize that there is a function inside a function, and the outside function happens to be the square. So I say that we have this square is the f function, and then inside this function you have x squared plus 1, which happens to be the g function. If g is, and then you can check whether you actually pick the right functions, right? You can easily make the silly mistake and pick the wrong function to be your g and your f, but you can easily verify that you did this correctly by taking the derivative of g. Take the derivative of g. The derivative of g is 2x plus 0. And there you go. So it does, right? So you do have the derivative of g as a product. So it seems like everything is checking off. So let's go ahead and do the antiderivative. Once we recognize the outside and the inside, we're going to sort of apply the technique that we discussed before, which means this will equal the derivative of the outside function, which happens to be a square. The function square is your f. So what do? We add 1, because it's a square, that means it's a power. We have to use the power rule for integration, and the power rule of integration states that we have to add 1 to the power and divide by a new power. And what do we do with the inside? According to the problem, it says leave the inside as it is, right? Leave the inside as it is. All you have to do is just change the derivative for the derivative of the outside, and then you add c. So I hope that this is sort of kind of making sense. We're gonna have a few more problems for us to try, like example number 2, practice number 2. So here we have a integral of 5 times cosine 5x dx. Obviously this is part of the trig, and so the solution is found, and this is going to be the solution. So we're going to take the integral of this. Now if we're going to take the integral of this, we must have an outside function and an inside function. Well, right away I only recognize that there is only one function inside another function, and that is going to be 5x. 5x is inside the function of a cosine. So that sort of already tells me that if this is going to work out, that this is going to work out whenever g is 5x. If g is 5x, that means that g prime needs to be 5, and it is, right? And so I've sort of rewrote that by moving that over here. So that will be 5 dx. So there you go. So the outside function is f, the inside function is 5x, and the derivative of g is 5 dx. So the rule says all you have to do is take the derivative of the outside, the antiderivative of the outside. The antiderivative of cosine is sine. Leave the inside as it is, and you're done. Obviously add the c. Alright, so the integrand in example 1 fits the f of g of x times g prime of x pattern. Exactly, right? As it's stated. but you only had to recognize the pattern to be able to apply it. So you can extend this technique considerably with a constant multiple rule. So I remind you that in the previous sections we discussed this constant function rule, and the function and this rule states that you are able to factor out a k out of the integral without changing the value. So that means if you have a constant here, you can factor it out. Many integrands contain the essential part of g prime of x, but are missing a constant multiple. So what's going to happen, a lot of times the g prime of x will be there, but it will be missing a factor, a constant, right? It will be missing a constant coefficient. So a lot of times this would work, except that the g prime is not exactly as it needs to be. But what this rule is suggesting is, hold on, we can manipulate the original function so that this can happen. And I'll show you guys a few examples where we are doing we're doing that. Okay, so the next example, we need to multiply and divide by a constant. Find the antiderivative of x times x squared plus 1 square dx. The solution, this is very similar to the integral given in example 1, except that the integrand is missing a factor of 2. So recognizing that 2x is the derivative of x squared, we can conclude that g of x must be x squared plus 1 and supply 2x as follows. So what we're going to do here, and I want to remind you guys about the technique that we use often, is recognize first what is the inside function and what is the outside function. So here, I always drive myself to the parentheses most of the time. I'll say a good amount of time that's sort of kind of like a hint. So I see parentheses here. So my guess is that this needs to be a g, my g function. And then the f function is going to be the square function, followed by multiplied by g prime. Now, when I try this, obviously I'm going to move my x over here by just switching the order of the factors. But I notice that the parentheses here have x squared plus 1. So that sort of kind of gives me a hint that that will probably be g of x. So what we're going to do here is we're going to take the derivative of this, which is 2x. Now 2x must be outside as a factor, but if you notice, the 2 is missing, right? 2 is missing, and it would have been perfect. Everything would have been fine. This would have been your g, the square would be your f, and the derivative of g would have been 2x. But we don't have the 2. Well, in the next line, we go ahead and do that. We actually gonna multiply x by 2 by dividing also by 2. This way, we're not changing the value of the integrand of the inside, right? We're not changing the value of anybody. But by doing that, now we have this extra constant of 1/2. No problem, we can just factor it out. So therefore, we have 1/2 times the integral of x squared plus 1 square times 2x dx. And now we notice, here's your g, here's your f, here is your g prime, and so that's gonna give us the integral of that will be the antiderivative of f. So we add 3 to the power of 2. So sorry, we add 1 to the power of 2, so that gives us 3, and divide by the new power. So therefore we get 3, so x squared plus 1 to the third over 3 times 1/2 plus c. And then from here we can proceed by simplifying the expression and multiplying the denominators to be 2 times 3 is 6, and then for the numerator it's going to be x squared plus 1 to the second plus c. Alright, and there you go, right? So the point of this was look for the pattern, but if the pattern is not there exactly, in fact is missing by a factor, that's not a problem. We can actually manipulate the algebra to make it exactly what to fill in exactly what we're missing. Okay, so now we're gonna try a different approach, right? Or it's the same approach, it's just a different steps. So instead of leaving this to a pattern and trying to guess what are you missing, we can actually do this by using U substitution. Now there is different approaches of U substitution, and I can share both of them. They're gonna give us the same result. There's just maybe a tweak to it from one to another. They're very similar. It's just one little tweak, but either one will be great. So let's start example 4. Let's change variables. So the change of variable real quick is for times where you actually are changing the function in terms of u and the derivative in dx in terms of du. So everything is turned into u to make it look like it is a simpler function. So and we're gonna be following this, right? So it will be the integral of f of g of x times g prime of x dx equals the integral of f of u du, which is the integral of uppercase f of u. So what we're going to do here is first recognize what is your u and what is your du. So because I see a power form and I see power and I see parentheses, my intention is for me to make this be my inside. I'll let that be my inside part of the function, and the outside happens to be the power 1/2. So you have a power to the 1/2. Well, what are we missing? Well, if you do the derivative of 2x minus 1, if this is your inside, then that means that your derivative needs to be over here, which is going to be 2 delta x minus 0. So there's your delta x. Then, if you notice, the derivative of 2x is 2 dx, but we're having this 2 extra, right? So we need to remove that 2. Now, don't forget that this is a 2 from the denominator, so you have to rewrite it as a 2 from the denominator. So you're going to have to put a 1 on top over the 2. Now that you do that, now you can go ahead and replace this with u, right? This is going to be where the process is going to start. We're going to write this in terms of u, so this will be u to the 1/2 times, if you notice, when you take the derivative of 2x minus 1, this gives us 2 times dx. And this is exactly what needs to be going here. So when we look at this now, this is u to the power 1/2, 2 dx is du, and then we're still taking the integral of this and multiply by 1/2. So now the problem looks much easier. It looks more doable. It looks more simple. It looks more familiar. So now let's go ahead and apply the antiderivative. Now remember that these are in terms of x. These need to be all in terms of u. So we'll do the antiderivative of u to the 1/2, and that's going to be you add 1 to the power and divide by the new power. And that's the rule of power, right? Power rule. We'll multiply by the reciprocal of the denominator, so that will be 2 over 3. The 2's will cancel each other out, and then we're left with 1/3. And then so we simplify everything. We have 1/3 times u to the 3/2 plus c. And so now at this point, we're going to go back and replace u in terms of x. So that would be 2x minus 1. So there you go. We end up getting this result. And we can apply the same technique for practice 5, practice 6. The same argument, we're going to use u substitution and then apply the antiderivative and then go back. So these are some guidelines. I promise we get to do more of this, right? So I'm just going to do some guidelines and then we'll practice a few more times. So some guidance for making a change of variable is to choose a substitution of u. And that means find what needs to be substituted to u. And that tends to be whatever's inside parentheses, whatever happens to be a power, right? And then usually it is best to choose the inner part of a composite function such as quantity raised to a power. Then you're going to compute du equals g prime of dx times dx. And then we write the integral in terms of the variable u. And we write everything in terms of u. And then find the resulting integral in terms of u. Then replace u with g of x to obtain an antiderivative in terms of x. Check your answer for differentiation. So that's sort of the guidelines. Now we can generalize this guideline with the next rule, the general power rule for integration. So just remember that the general power rule is applying the same technique that we used before, except that this technique is specifically used for functions where we can actually find the actual values. So one of the most common use substitutions involves quantities in the integrand that are raised to the power rule. Because the importance of this type of substitution, it is given a special name, the general power rule for integration. So in theorem 4.14, it states that the general power rule for integration, if g is differentiable function of x and g of x is if g is differential function of x, then the antiderivative of gx to the power of n times g prime of x is going to be the function g to the power of n plus 1 over n plus 1 plus c. So what we're saying is that if you have the case where we're doing power rule and you identify the inside function, then pretty much it's just going to be the same thing over and over again, right? You're going to raise this to power 1 and then divide by a new power, and then this goes away. And it works with the u substitution as well. So let's try a few problems. So u substitution and the general power rule. So what I did here is I sort of as an exercise, I found what was my inside function. So that was 3x minus 1. I noticed my outside function is the power of 4. Now what I did here was then we have the derivative of this will be 3 minus 0. So that pretty much tells us that our differential of u will equal 3 times x. Alright, so part B. Alright, so sorry, I didn't finish this one over here, sorry. So this is the 3. We replace u with 3x minus 1 with u to the power of 4. And then this is dx. So what we're going to do here is we're going to replace this with u to the power of 4. This with this gives us 3 times dx, which is du. Now I did something here in particular, sort of kind of neat. It's a little technique that I've learned through others. But what I tend to do here, so that I don't have to worry about this 3 and compensating for that 3, what I tend to do is actually solve for du for dx. I try to solve for dx because this needs to turn into a u. I solve for dx all the time, and then whatever I get, which will be dx equals du over 3, then that's gonna be going in here for dx, right? So when you replace it here, you're gonna replace dx with du over 3. The 3 and the 3 will cancel each other out, and so you're left with this. Now for this, it's simply using the power rule, right? Add 1 divided by new power plus c, and then 1 over 5 times 3x minus 1 to the 5th power plus c. So no whatsoever, no issues. All right, so part B, we have a product, right? We have 2x plus 1 times x squared plus x. Now the problem with this, and sort of what I want you guys to think about, is the question most likely you guys will have if you're trying to solve this is, which one will be my inside g of x and which one will be my outside? Now, to be honest, it's hard to tell just by looking at them. What I do is I do both derivatives. I do the derivative of the first one, and I see whether the function is there. If I'm checking so if I'm checking whether the derivative is there, right? So if I check the derivative of this, the derivative of this will be 2. The derivative of this will be 2x plus 1. So if you guys notice, the derivative of this is here. So I see my derivative here of this. So this will be a function inside of the power 1. So therefore, what I'm going to do in this example is I'm going to let u be x squared plus x. And then I'm going to do the derivative of this, which will be derivative of du over dx, which is derivative of this will be 2x plus 1, multiply both sides by dx, sort of kind of like a silly thing to do. You can just jump in from here to here, doing differentials. And then divide both sides by 2x plus 1, so you can isolate your dx. And so what we have here is we du over 2x plus 1 is equal to 2x. So we're going to go back, replace this with u, replace dx with du over this. These two will cancel each other out, leaving us with the integral of u times du. Then we do the power rule, right? To do the antiderivative of this, we apply the power rule, which will be add 1 divided by new power plus c. And then this will, after this, we'll go back and replace the u in terms of x, which we know is x squared plus x. So we square that and plus c. I want to remind you guys to make sure to carry your integral, right? We're just sort of fixing the problem before we apply the antiderivative. That way it's just easier for us to do. Let's try another one. So here, the next one, we're gonna go ahead and recognize that the inside of this will be the one inside this radical. So in this case, it will be x cubed minus 2. So that's my du. Find the differential by doing the derivative of this. It will be 3x squared multiplied by dx. And so we already have that this is going to be u to the power 1/2. We have 3x squared, and then we have du. Dx needs to be turned into a du. So what are we going to do? From here, you need to turn the dx into terms of u. So divide both sides by 3x squared. Divide both sides by 3x squared, and that gives us dx is equal to du over 3x squared. And then we'll do that. We'll replace dx with du over 3x squared. Notice that 3x squared and the 3x squared cancel each other out. And then now you're left with the integral of u to the 1/2 times du. Now notice that we don't have to do any we don't have to play the game of guessing in this type of problems, and that's sort of kind of the benefit of u substitution. Now over here, when you add 1 divided by new power, we have to multiply by the reciprocal, which is 2/3, of the inside to the power 3/2 plus c. Alright, moving on to the next one. Here we have another case. If you guys notice, if you think about this for a second, what functions inside of parentheses, and obviously you guys can see that y minus 2x is inside of parentheses. In fact, is inside a square power. So that tells me that my g will be the 1 minus 2x squared. And so because I can double check it by taking the derivative of this. The derivative of 1 is 0. The derivative of negative 2x squared is going to be negative 4x. And I see that up here. Now, what I'm going to do now is I'm going to let u be this. Take the derivative, that gives you negative 4x. And then the derivative of my differential will be negative 4x dx. So I'm going to go ahead and go back and replace this with u, square that, replace dx with du over negative 4x, cancel those two together, and now you have du over this. And this is u squared. So we're going to move that to the top so we can take the integral and use the power rule. So we're going to have u to the negative 2 times du. We can take the integral of this using the power rule. So add 1 becomes negative 1 divided by new power, so divided by negative 1 plus c. But then we can come back and replace u in terms of what it was originally set up. So that would be 1 minus 2x squared to the power negative 1 over negative 1 plus c. And then from here you can just move this to the denominator, and we have this. Alright, next example is sort of the same idea. We have cosine square x times sine of x. We have to recognize which one is the inside function. So in this case, the inside function will be whatever's inside a power. There's a power square. There's a square power, so that's in, and cosine is inside that. So my suggestion will be cosine becomes the inside function, and square becomes the outside function, and sine of x becomes the derivative of g. So that's pretty much what we're doing. I will first rewrote it as a square function, right? U equals cosine. The differentials of u equals minus the derivative of cosine is going to be negative sine x dx. And then we're going to solve for dx by dividing both sides by negative sine of x. And we do that, and that's how we got dx equals negative du over sine of x. Then, so where we're gonna go back is we're gonna replace cosine instead. We're gonna replace cosine instead of with u. So you have u squared, and then we have sine of x times negative du over sine of x. The signs will cancel each other out. The negatives carry over to the front, and there you go, right? Now we have this, and we can take the antiderivative of that by applying the power rule. Add 1 divided by new power plus c. Replace at the end u in terms of cosine. Alright, so those are the basic techniques of integration by substitution or by pattern, right? We're going to extend this further. There's another technique or another special technique that we can use for u substitution, as we're going to see in the next line. So when using u substitution, which with a definite integral, it is often convenient to determine the limits of integration for the variable u rather than converting the antiderivative back to the variable x and then evaluate the original limits. So what we're saying here is the limits are always going to be dependent on this variable, right? So what we're saying is that if you use u substitution, then this will turn to be f of u and this will turn to be du. But b and a are still technically values of x. They're values of x. So what we're going to do is we could just rewrite them in terms of u, and then these values are u values. And so we are able to sort of simplify the process. Let me show you guys the next example. Alright, so we're going to do we're going to evaluate the integral from 0 to 1 of x times x squared plus 1 cubed times dx. So the first thing is first, let's go ahead and recognize what's going to be the u and what's going to be the rest of it, right? So let's try it. So u is going to be whatever's inside the parentheses. In this case, it's inside this power, so u equals x squared. Du is the derivative of this, which is 2x, and then we need to write it as differential, so du equals 2x dx. So you notice we are missing something from here, right? We're missing the coefficient of 2. We can do this by guessing, but we can also just use u substitution. So that's what I'm going to do. So I'm going to change x squared plus 1 to be u, and we're going to leave it to the power of 3. Dx is the same thing as du over 2x. Cancel the x's together, and that gives us this new integral. We can apply the power rule for the integral, and that will give us u to the 4 over 8, plug in 1, plug in 0, and this gives us sorry, let's go back over here. So these will be values in terms of x, but we cannot plug them in because this is in terms of u. Now you could turn this back into x by rewriting this in terms of x as x squared plus 1, or we have this alternative. We can change the value of our x's in terms of u. So we can replace this and this in terms of u. We already know what u is in terms of x right here, right? So what we're going to do is we're going to let x, when x equals 1, that means that u will equal 1 squared plus 1, which is going to be 2, which means that u equals 2. Then when we plug in 0, then we have u equals 0 squared plus 1, which is 0 plus 1, which is 1. So we end up getting u equals 1. So what we're going to do here is we're going to rewrite them. We're going to rewrite this in terms of u. So this will be u equals 2, and this will be u equals 1. So notice that now we can go ahead and plug them in. So now we have 2 to the power 4 over 8 minus 1 to the power 4 over 8. And then simplify this as much as we can, and that will give us 15 over 8. All right. Like I said, we could have done it 2 different ways. Here, we could have just changed. We can change them in terms of u as we did here, or we can leave them in terms of x, but we need to change this u in terms of x, right? And that's sort of what the single step that we're doing. You can try practice 9 on your own. The u substitution will be the value 2x minus 1. You're going to have to do some manipulation there, but I feel confident that you guys can try. Alright, so the next part is integration, even, and odd functions. So even with change of variables, integrations can be difficult. Occasionally, you can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis, or about the origin by recognizing the integrand to be even or odd function. So the following shows us the application of an even or odd function. Assuming that f is an integrable function on a closed interval from a to -8, if we actually have an even function, if f is an even function, what this is suggesting is that if we're taking the integral from -a to a of f of x, then this will equal 2 times the integral from going from 0 to a of f of x dx. And sort of this is what's happening. If you guys notice, if you're even, that means that you're symmetric here in respect to this. So this is equal to this. So if that's symmetric. So if those two are the same thing, well, why don't we cut it out from 0 to a, find this area, right, and then double it. And that's sort of what we're doing, right? We're sort of going, instead of going from here to here, as we did there, what we're doing is we're just gonna go ahead and divide it and do from 0 to a, and then double it to make sure that we get the entire area. So that's pretty clever, right? That's pretty clever. And it gets be useful when we do a lot of the trig functions, because those are easy for us to recognize when they're whether they're even or odd. The next one is the odd function. The odd function, if f is odd, then the function negative a to a f of x dx is equal to 0. And here's an example of it. So if you're going from negative to a, and that means you're symmetric to the origin, and so therefore you're going to have this space is equivalent to that space. Well, this one's positive and this one is negative, so when you combine them together, that will give you a net zero. Now I remind you guys that sine is an odd function. Sine is an odd function, so sine of negative x is equal to negative sine of x, and cosine is an even function. So that will help us determine whether which technique we're going to use. So let's go ahead and do that, right? So in the first one, we're going to check whether the original function f of x is even or odd. And we can do that very quickly. How do we check it? By plugging negative x into the function and make sure that we are getting back to the same function. So plugging negative x into sine of 3, that's going to be an odd function. So we're gonna factor it out, and then sorry. Let's go back over here. So let's check if it's even or not, right? So we're gonna plug in negative x, negative x, negative x, negative x, negative x for every x that we see, right? All right. So we are good with that. And then what we're gonna do is we're gonna check whether they're even or odd, right? So sine of negative x is going to be negative sine of 3x. Cosine is even, so that means that it absorbs the negative. Sine of negative x is going to be an odd function, so that would be negative sine of x. Cosine of negative x is an even function, so it absorbs the negative value. Now, if you factor the negative from both terms, then we get this sine of cube x cosine of x plus sine of x cosine of x, which, if you guys notice, is exactly the same original function. So therefore, this is negative times the original function, which means it's odd. So therefore, and because we're going from the negative value to opposite signs, then that means that this is going to give you 0. And there you go. You don't have to do anything but to show me that you're using this rule. All right. And so that the argument is sort of this, right? Of being an odd function, is that you have a negative value and a positive value. When they combine each other, they undo each other, so that's 0. All right, so here I'm going to do number 5 from above. Which one is that over here? All right, so we're going to do this problem right here, and we're going to be using U substitution, right? All right, so what we're going to do here is, this one's a special problem, so we're going to call this special problem, because it requires some special technique. And this is sort of kind of opens the doors to other techniques, right? There's more techniques that we can do, but this is one very common. And I expect you guys to be able to master this one. So if I do, the first thing is rewrite this in power form. And then I recognize that what's going to be my g function. My g function is going to be this. My derivative will be 2, just 2, right? 2 will be my g prime. If you notice, I actually have more than 2. I actually don't have the 2, right? But I can do that by multiplying 2 over 2, and then factor out the 1/2. So that's no problem. That's not my issue. My issue is here. That x right there. In fact, when those two are matching each other out, that's sort of kind of some heads up that we're gonna have to do some special problem. So what I'm gonna do first is I'm gonna go through the bases. I'm gonna say, okay, u is gonna be 2x minus 1, what's inside the parentheses. Du is going to be the derivative of this, which will be 2 dx. And then I can go ahead and start replacing stuff, right? I can say this is going to be u, this 2 dx is going to be du, but if you notice, x is sort of left out behind, right? That's not going to be we're not going to be able to write it in terms of u. Wait, we can because we can use this and solve for x, and then that will give us everything in terms of u. Let me show you what I mean. You have add 1, so you have u plus 1 equals 2x, and then this implies by dividing both sides by 2 that u plus 1 over 2 is equal to x. So therefore, if we are once we found the x, we're going to replace it here. So we're going to replace it there. So we have u plus 1 over 2, that's your x, your xx. The 1/2 is still outside, the integral is here, and we're going to replace this with u. We still have the power of 1/2, and then 2 dx is du. So there you go, right? Now we have a new problem, but you guys thinking, wait, that doesn't make this easier. It kind of does, because now this is a single value that we can actually spread out, right? We can distribute. This 2 can be moved outside and be multiplied to the 1/2, sorry. So that gives us 1/4. When you multiply 1/2 times u, that gives you u to the 3/2. When you multiply u to the 1/2 times 1, it gives you u to the 1/2. And then after this, then we can just use the normal antiderivative, which will be add 1, so it'll be 5/2 over 5/2 plus u to the 3/2 over 3/2. And then we divide by the reciprocal, meaning multiply by the reciprocal. So it'll be 2/5 times u to the 5/5 plus 2/3 times u to the 3/2 plus c. And then we're going to go ahead and distribute the 1/4, and this will cancel each other out with giving us 1/10 times this. Replace u in terms of x, that'll be 2x minus 1. This 1/4 times 2/3 gives us 1/6 times 2x minus 1 to the power of 3/2 plus c. So there you go, right? So we are able to find the antiderivative. Now the technique was this. This is the special part, and maybe I want to make it more obvious for you guys. So this is the special part right here. The fact that we're able to find x because we needed x. Okay. All right. So I hope that you guys find this helpful. Please let me know if you have any questions. I'll see you guys next time.